right, here we go. Thank you for reminding me.
Yep.
All right, yeah. So that should be going now. Let's see. So okay. So now let's get back to screen sharing. If you can, let's see. Okay, share. Just hit share. All right, there we're back. Are we back? I think we're back. Okay. Um, so now so we want some prediction rules for the various Fourier series. One special case, which is often overlooked as being a Fourier series, because hardly to call it a series is not quite right. But if there's only one term and it's a sinusoid, it's still periodic, and you could say, well, it's a special case of a more general Fourier series. We're going to actually do that. We're going to kind of bootstrap ourselves to the series by looking at the response to a sinusoid. Okay, it turns out that serves its purpose. Ultimately, the idea would be to carry the concept so far that we can actually ask what happens if you put the signal through a low-pass filter. Now, you could argue the ideas as they're introduced aren't really limited to being a low-pass filter. You could argue any filter, whether low-pass, high-pass, or bandpass. But the point is, in many ways, the low-pass filter is one of the simplest of the bunch. So that's what we usually do. So in order to move the ball a little farther down the line, so to speak, we're going to have to remind ourselves some of the formalism that we had seen in the earlier chapter, I believe in the chapter 2 notes. It's also in the text reference given. And one way, some people view this as one way of defining the transfer function is that if the input is this, what they call a complex exponential e to the st, then the form for the output would be that same input, but multiplied by the transfer function. Okay. Now, this is has a little more general than what would be practical for us, because the frequency components, the frequencies that are needed when a Fourier series is discrete, and therefore what we can do is, they are, you could argue if you look at any one of them, they don't represent transients, they represent sinusoids. So we can let S be equal to j omega as initial step. Ultimately, we'll make them discrete. But let's, for right now, we'll just recognize that the individual terms in the Fourier series are just sinusoids anyway. So we can say when we're looking at any one of them, we can let S equal to j omega. And so to essentially summarize that, we'll say, okay, the special case of the more general formula that we've seen before could be just simply written down by letting S equal to j omega. And then, of course, our transfer function, here the S was replaced with j omega also. So I can do it here maybe. Okay. So we're going to start the ball in the following way. Our first step would be to look at the response of this system to a simple sinusoid. Okay. And so we'll take, let's say we take the cosine of omega t, and that, of course, is a simple sinusoid. And if we multiply by 2, we know according to Euler, we can just simply write it that way, sum of 2 exponentials. Let me blow that up a little bit. It might look clear. Let me go to the slideshow. Okay, so really no magic here. It's just using the formula for breaking up the cosine into complex exponentials, and then if I multiply by 2, we just made it a little simpler by, so we got rid of the 2 in the denominator. Didn't have to do that, but it just lightens the notation, so to speak. So we can, in predicting our output, we can remind ourselves that the transfer function in general will be complex. So we can represent it in polar form as a magnitude and a phase. And I would argue that you may already be familiar with the fact that these are two ways to also are equivalent. In other words, this part right here is, you could say, well, this is telling us what the phase of the transfer function is at a certain frequency, but we would, if we were going to write it out in more general ways, in polar form, it would look like this. But both are usually considered carrying the same information. So in one step, we would argue we can get the response to the system by applying the superposition. In other words, because this is LTI systems, we would argue that the operation on the sum would be the sum of the operations. So we could say, well, whatever the output for the first, we can analyze this by looking at the individual terms. So we already know what happens to the e to the j omega t. And we would say, well, it's pretty much the same thing happens to e to the minus j omega t, just replace omega with a minus omega. So you see where you get the first term and get the second term. You say, where did that come from? And that was from the previous page. From down here. But now we're applying superposition because we broke up the input into two pieces. Okay. Any questions so far? All right. Now at this point, what we want to do is we want to insist essentially that if we're a physical system, we're putting a real signal out, we get a real signal in, we get a real signal out. Of course, we know that even though this representation has j's in it, if we work backwards, it's strictly real. So we would argue that our response should be strictly real. Now, by virtue of that requirement, we can remind ourselves of the complex arithmetic rule that if you add a complex number to its complex conjugate, the imaginary part cancels out, it's 0, the sum of the two. So since we're arguing that y of t has to ultimately be real, it has to be that the first term, let's say we called it z, the second term has to be compliant with this rule and has to be the complex of the first term, complex conjugate of the first term. Now, to repeat an idea we've seen in another context, but still same idea, we can immediately see what about the complex exponentials e to the plus j omega t and e to the minus j omega t, what they are. I'm looking for someone to speak up here. What can I say immediately from observation purposes? How are they related? They are
complex conjugates.
Complex conjugates, correct. So in order for us to satisfy this condition with these two, all that's left for the h's that we see here is they must be complex conjugates. So in other words, the one way to view this is the second term h must be the complex conjugate of the first term. That's the one with the minus, must be the complex conjugate of the first term. Now, buried in this condition, since we're talking about complex numbers, of course. Really, there are two conditions you can extract, and I use this sort of kind of a general argument to support that, so it doesn't get you're not distracted by the details of the omegas in the symbology. Let's just say if we had two complex numbers, and we know that A is equal to the complex conjugate of B, we know that they are then their magnitudes must be the same. Okay, you can always convince yourself of that by putting them in polar form. And we know that if we take the magnitude of a complex conjugate number, you get the magnitude of the original that's not complex conjugate. So in brief, what we're saying here is that the magnitude of the left side must be equal to the magnitude of essentially the right side, of course. But we also know the magnitude of a complex conjugate is the same as the magnitude of the complex of the non-conjugated quantity. And from that, we can argue that these transfer functions have what would be called essentially an even dependence on omega. And what do we mean by that? Remember, if you said f of x and f of minus x is equal to f of x, you know that's even. So you could argue here we're looking at what would be called an even dependence on the frequency, omega. And that's characteristic of all these transfer functions. Okay. Now, as far as the second half of the story is, which, like I said, the second condition you can pull out of this result is that there's a relationship between the phases. Okay. Now, what's in the box tells me, okay, the phase on the left. Okay, well, let's go run through this one real quick. So if these two quantities are equal, then they must have the same phases. However, we know the phase of the complex conjugate is minus the phase of the unconjugated complex number. So we see, in fact, if you want to think of it this way, then the phase or angle associated with the vector, the complex number A is minus the one associated with the complex number associated with B.
So what does the asterisk stand for?
That's a complex conjugate operation.
Oh, okay.
Replace J with a minus J. Like the same thing is up here. I'm not sure. Maybe I should have answered that question back up here. So, for example, A plus JB, then the complex conjugate of A plus JB is A minus JB. Everywhere you see a J, replace it with a minus J.
Okay.
So, no. And so if we follow the kind of like the basic rule here, just in terms of A and B symbols, but apply it to this situation, we would have to argue, first off, since equal signs means whatever's on the left is equal to whatever on the right. Therefore, the phase on the left must be equal to the phase on the right. No hidden agenda there. However, then we also would remind ourselves by taking the complex conjugate of the quantity, you essentially get the opposite phase. So you have to throw a minus sign in for that. So basically, then in the end, we would argue that we've come up with an odd functional dependence on omega, right? Because remember, if you said, well, replace x with a minus x, if it's odd, you get a minus f of x. We talk about odd and even functions. And so, yes, we replace omega with a minus omega, we get the minus of the phase. So the phase has an odd dependence on omega. Any questions on that? Let me see if I can't just move that down here a little bit. Oh, yeah. Now, where we're going with this is we want to simplify as much as possible to draw a conclusion. And that's, in the end, that's kind of where we get the big ideas, hopefully. All right, so we up at the top, we started with this just by direct superposition. We applied that. From the symmetry, from the symmetry, and I've used here this notation just to lighten it a little bit, so I don't have to write all that out. So what this means is this: theta subscript h is the angle associated with h. So where normally you would essentially say the angle here, but simple, but you can just write that e to the j theta sub h. And all we did was take that general expression for the h at j omega and write it in polar form. And then we do it for the h of a minus j omega, we write that. In writing that in polar form, we can in fact use the symmetry properties from up here, which says that the magnitude is an even function. Therefore, we can the magnitude dependence on omega, replace omega with minus omega, you get the same quantity, so we can just drop the minus sign. On the other hand, the phase, the phase that we would get here is the complex conjugate. Is being the complex conjugate will give us, in fact, minus the phase that we had here. Now, the symmetry rules play an important role here, because what we ultimately want to do is we want to reverse the unraveling we did at the very beginning. Now, I'll remind you that in the very beginning, we started off with a real, whoops, let me get there. I'll remind you, we start off with a real function, slightly simplified by multiplying by 2, so we didn't have to carry that extra 2 around. The only reason could have been carried. And then so we want to go back and reverse that to get another real function, represent the output as a real function with no j's. And that can be done, or I wouldn't be bringing up the issue, right? So we're going to kind of go back, and then we'll draw a conclusion. So in looking at the form, we see, in fact, the magnitudes that we see here for the transfer function at j omega are going to be, of course, as shown, they're the same, so they can be factored out from the terms. Now, we can also recognize that when you, what do you do when you multiply? What do you do the arguments when you multiply two exponentials? Anybody?
Add.
You add them, right? So you add those exponentials, and notice there's a common factor of j. So you're going to get omega t plus theta sub h. You could do the same thing here. Again, a common factor not only of j, but a minus sign. And you can factor out the omega t and the h. Now, to put the icing on the cake here, what we need to do is multiply and divide by 2. So we can recognize this looks like the standard form for the what function, sine or cosine?
Cosine.
Cosine, right, yeah. E to the jx plus e to the minus jx divided by 2. In this case, this is rx. So we can just simply say, we get 2 times the cosine of omega t plus theta h with that magnitude of j omega factor in front. Now this is the point where, okay, you say, well, what was the conclusion that you can say, well, that makes sense if you think about it. What we're saying is, let's say we had this system that we put the sinusoid into, and then, like say with the oscilloscope, we measured the output, again a sinusoid as we see here. And what we would find, remember 2 was originally in the amplitude of the original input, so I don't have a problem with that. So what we find is the actual amplitude of the output sinusoid was in fact scaled up or amplified by the magnitude of the transfer function at the frequency of the sinusoid that went in. And of course, what we're seeing here is you get the same frequency out, but we also, so that was one effect, was on the amplitude, and what we see here is the magnitude of the transfer function affected the amplitude on the output by exactly its magnitude, and then we can introduce a phase shift. Okay, right there. So notice the plus theta sub h. Any question on that? Okay, so in the end, the conclusion is amplitude is scaled by the magnitude of the transfer function, specifically at the frequency of the sinusoid going in. And second, it's phase shifted by exactly the phase of the transfer function as we see it here. And you say, well, that's what you'd expect if you looked at the output on an oscilloscope. And you put it through some kind of filter. All right, so. Okay, now. Yes, let me blow that up a little bit. Now I went through that, and you could see, well, there isn't much difference if you here I have an arbitrary A. In the previous example, I had 2, and there was no phase shift built in on the input side. Well, the steps involved, breaking it up and working out the details is really pretty much the same kind of steps, and I put that at the back as the appendix. Because I think it won't be that exciting to go through it anyway. So, but here is a conclusion. If we had used this as our input, and again, the pages should be at the back of the notes on the details if you're interested. It's the same it's the same steps. It's just a little more complicated because the theta was included and the A was not equal to 2. But if you go through the steps, what you're going to find is pretty much inclusion is the same. Notice that the output has been exactly scaled by the magnitude of the transfer function at the frequency of the input. And as we see it here, you get the same cosine, but only shifted by the phase shift associated with the transfer function, again, at the frequency of the input. So, the conclusions are pretty much the same. I mean, it's just that, you're dealing with a little more general form for the input on the input side. But if you look at what happens on the output, it's absolutely consistent. Okay, so I'm trusting you don't want me to go through all those details because they're very, very similar. Is that true? Is that okay? So I'm thinking if you're interested, you can look at it. I won't ask you to prove it on an exam. But I think it's you can see that I think you can see that this is pretty much very close. If you set theta equal to 0, and if you set A equal to 2, you're back to the other problem, the one we did, the simpler one we did. Okay, let me go back down here. Now there's some special cases that, okay, let me make a quick comment. When it comes to the compact Fourier series, this is the one that's going to be the most helpful for us. Okay, so we'll actually go back to this one right here for the compact. Maybe surprise, surprise. It's more or less the terms of the compact Fourier series are all of them in pretty much kind of that kind of form. So that's why it's such a good match to the compact Fourier series. Now, when it comes to the basic Fourier series, which are pretty much sines and cosines without a phase shift, we can come up with actually a little more useful, directly useful rules, which pretty much are spin-offs of the one up here at the top. And then once we have those written down, what you'll see, it's very helpful for the prediction what happens to the basic Fourier series. Okay, but I mean, that's it. Yeah, but you will. Okay, so I'm wondering, is this you can see you see my pointer? Is it out there? Everybody, anyone? Can you see that? It looks like a hand or a pointer.
Yeah, we can see it.
Yeah, okay. But are you being blocked on the far right or not? Because let me see if I can.
Are you talking about the thingy?
Yeah, okay. Oh, now I got it moved out my way. I can now see it. All right, that's good. I guess even if it was blocking, I fixed it. So, all right. Okay, so let's just say that our input is simply a cosine as we see it, no phase shift, with an amplitude A. If we go back to the top, that would correspond, as you might guess, to setting theta equal to 0. Okay, and that would, so if that means theta is equal to 0 here, it's theta is equal to 0 there. And so this part follows from the general rule, and the rest of it looks the same. Now, that'll be helpful to us when we do the coefficients with the cosines. All right, let's go down a little bit. Now, to get the one that we're going to need for the sines, okay, now the one we're going to need for the sines, I'm going to remind you of this trig identity. Okay, and we talked about it I think a few lines. I remember there one of the pages we had this on there. And so we're interested in the signs. Okay, and so imagine we're primarily what it means is if it's a plus, let's say we have plus, then we should be using the minus. So I would argue that if you just pull that guy up, I'll let you prove it offline, but there's the trig identity for this is a few pages back. We did cover it. Then if you say, well, can you represent that sine of omega t with a cosine? And of course, the answer is yes, or I wouldn't be raising the question. And we see since it's a plus in front, this is the amplitudes, which are always positive. It's a plus in front. I really want to use a minus 90. All right. So if we go back to our original general result at the top, I would conclude that, let's do that for a moment. If we go back to our original general result at the top, that would correspond to setting what? That theta equal to what? Anyone out there, you're following me? What am I going to set it equal to based on this? I'm thinking about my x of t being a sine, but if I represent it with a cosine like this, what is the correct theta I should use? That's my question.
Pi over 2.
Yeah, well, let's see, according to this, you're almost there. It's, I believe, a minus 90, which would be a minus pi over 2. Let's go down and see what I'm going to see. See, it's actually to get since it's plus in front, you need the minus, right? Because that's the consistent with the vector identity. So you need a minus 90 degrees, not plus, but you're close. So that would be the general result. So now since we've identified the correct theta that we would need in the output, all we need to do is then go to the corresponding general result for the output and use that value of theta, which is right there, in the expression. Ooh, did that wrong. Okay, let's go back. That's the next page, actually. All right, there it is. So yeah, so if we go back to there's the general one, right? So if we set the theta equal to a minus 90. And there it is. Of course, addition is commutative, so a plus b is b plus a, so it doesn't matter what order that is. Okay. And then the idea would be, well, it may not be too shocking. This vector identity, okay, can still be used and used effectively here to go back to a sine function, right? Because you can just say, well, in this case, all of this is my oh boy, I didn't realize that until just now. Okay, so I need to clarify one thing. The A, and maybe somebody realized that, the A used here is an angle not connected to the A for the amplitude. So just bear that in mind. If you have a question about it, hit me about it. But the A's are not the same A. I mean, this is part of the trig identity, and this is the amplitude of the sinusoid. So, but imagine that we essentially lump all of that together and temporarily give it the symbol A. then we see that if it's a minus 90, you've got to use a plus. So you end up with essentially this expression where in fact we got rid of the cosine, got it back to a sine, which is kind of nice because originally you start off with a sine function. And our conclusion was, okay, that in the end, our output was just essentially just like you'd expect. It was the magnitude of the transfer function at the frequency in question, keep the sign, and the only phase shift that took place that we see in it is in fact the phase shift due to the system transfer function h, just like here. So you could argue that the cosine went to the cosine phase shift plus phase shift. Sine went to the sine plus phase shift. So it makes it really simple if you want to represent the Fourier series in the basic case. It turns out to be helpful. Any questions on that? And again, I remind you, the A here is not the same as the A for the amplitude. They're two different A's. This one's for angle, this one's for amplitude, but whatever. Any questions? Ooh, let's see. So we talked about what we need for the compact, what we need for the basic. Now let's go take a look at the complex exponential. Okay, here is representation for the complex exponential Fourier series. How we proceed is just right out of the book, pretty much. We know that according to our rules, if this is my input, this would be my output. Okay, so essentially it reproduces think of that as S, e to the st, and replace the S with j omega in the transfer function. And so if we do the same thing, since we got the sum is running over negative indices, positive negative infinity indices to positive infinity indices, we have negative n and positive n. So one would argue we need to be ready to look at the case where there's a negative sign in front of the j. So if there's a negative sign in front of the j, we would write it that way. So I'm using again our old friend, the symbol for the operation. The operation on the input of the x of t being, let's say, this function here, produces that form. Okay, using symbol operator notation, and we can make this particular argument specific to the Fourier series chapter by replacing the omega with n omega naught, wherever we see the omega, the harmonics. Now that's going to be true for both the negative n and the positive n. So we don't need to really break these out at this point. So if we operate on that input Fourier series in exponential form, we would say in terms of number of steps, we would say, well, this is an LTI, linear time invariant operation. And because of that, the operation on the sum is looking for an answer here. Anybody listen?
Some of the operations.
Some of the operations, so I can move it past the sum. And we also know the operation on the scaled input is the scaled factor times the operation on the input. Okay, so basically I can move past, don't forget, even though they're complex, they're still constants. So these d sub n's have no time dependence, so therefore they can move, you can move that operator past them just like you would any constant, and just work on allow it to operate on that part of the signal which has time dependence, which is all buried in those exponentials that we have. So repeating most of this would say, okay, all we then need to use is this result from up here. If you follow me, hopefully. And here is the kind of the punchline. We see that in fact, complex number there's no time dependence here. You can view that's also complex numbers. So product of complex numbers, still a complex number. So you could redefine on the output side the exponential coefficients for the y of t. And notice once you do that, they'll again depend on n. And where omega naught appears, it appears as n omega naught. And you've got e to the j n omega naught t, which proves the point that the y of t is a Fourier series with the same period, which means the same fundamental frequency. Okay, and it's of course periodic. Any question on that? Oh, I keep doing that. Go back. Oh, we did that one. Okay, now this is the page we were on, right? So let's go, let's see. And we, all right, so this is just summarizing what we already know. The transfer function, okay, we never had it that way before, but you could argue that if you look at the expressions that we come up with, and we know that the magnitude was an even function in omega, and so you could say, well, the omega is equal to n omega naught. So in many ways, we swapped out the dependence on omega with a dependence on n. So you could argue that what that leads to, and would be the correct conclusion, that you could say, well, the magnitude of the transfer function is also an even, when written in this way, discrete frequencies, has an even property of n. And what do I mean by that? Well, if you replace n with a minus n, it's the same magnitude. Okay, that's like when you replace x with a minus x, f of minus x is equal to f of x. On the other hand, along the same lines, which where we had the odd function property for the angle, we could argue that replace the omega with n omega naught. So we see that if we use a minus here, then the original phase gets essentially changed by exactly a factor of a minus. So again, using our old definitions for odd and even, in this case odd, I would say if f of x is a minus f of x, f of a minus x is equal to minus f of x, then we have an odd function. So it's an odd property in n. Now remember that, especially on this page, what we're seeing is the n's can be both positive and negative. Notice it goes from minus infinity to infinity. So this business of odd and even are particularly relevant for the complex exponentials. Did I manage to confuse anybody out there? Am I going too fast?
No.
Okay, well, you don't stop me, I keep going. Oops, I don't know why I did that. So let's next page. All right, here we go. We're at the next page. Okay, so so what we got on the previous page was in fact a rule for predicting y of t for the complex exponential. So we're now going to, it seems like we're doing reverse. We're now going to do the compact and the basic on this page. But we're all set up for that. And we did the homework to be set up for that. So so let's first do the compact case. All right. Now here's our x of t. And again, we'll say our operation symbol refers to this system up here, for which we know the transfer function. And it's an LTI system. So we're going to claim that the operation on the input, here's our input Fourier series in compact form. The operation on the sum is a what? Since it's LTI. Waiting for an answer. The operation of the sum is the
Some of the operations.
some of the operations. So we can apply it to this, to the DC term, and we can apply it to the sum of terms here. But again, you could say ultimately we can move that, since they're also a sum, we can move that operation past the part which is a constant and directly only on the part that has time dependence. Now, believe it or not, we've actually spent a fair amount of time on that. So this one's already actually a slam dunk. But the first one I want to take out a minute for, which is the DC, which may be obvious, but let's just take out a minute for it anyway. So I would argue when you have the DC, okay, the DC term, which is a constant, that is as if if you want to think of it this way, if we set S equal, imagine I put in the constant 1, right? If I set S equal to 0, I got the constant 1. So what that says is to get 1 here, or if I set S equal to 0, get 1, that means I got to set S equal to 0 there. Now, our input here, you could say, is not 1, but I can always move that constant out and replace that with a 1, but it'll still be C0 times the operation on the number 1. Okay, and I contend that means it's a constant in the result from the operation on the constant 1 would just simply be H at DC. In other words, you evaluate the transfer function at omega equal to 0. So that would be my first term. And pretty much I needed that just to fill out the story. Now, why the rest of it is a slam dunk is because this is why we took out a few minutes to do it. On the previous page, we found out if we have an LTI system and this is our input, this is then the form of our input, right? So that was, we did that. We actually, when I say we did it, we did the simpler version, and then I claimed this would be the result we saw on the previous page. So now the only difference between this result and what we need is, well, we need to realize that we don't have omega here. We got the discrete frequencies n omega naught identified by the particular n. I didn't write n equal to 1 there, although I could have and should have. But anyway, the n is the index here, just in case you're wondering. So all we need to do is take our result from the previous page and apply it to each of these, where we've replaced the omegas where they appear with n omega naught, and the rest of it will pretty much go along for the ride, I think. Except I left off. I notice now I left off the n there. Let me make a note on my notes on that. Yeah, I seem to put it back in there. Okay, so I think it's it right there. So I think I'm going to circle that, and later on I'll subscript that with it. We'll be okay.
Where at?
All right. Any questions so far? So we have the Fourier series for the oops. I actually got some more time. We got the Fourier series for the output in the case that the input is in the form of the compact Fourier series. And yes, it's on the output, it's also compact. Any questions on that?
I had a question.
Yeah.
So we say y of t is an LTI system, but it contains cosine. So how does that work? In like the summation?
Okay. Well, I mean, we use the properties of LTI to get here. That's kind of how it worked. But I would say if you look at the output, the information that it's LTI isn't exactly just by itself isn't there. I mean, you have to actually say, well, how did you get there? And it really goes back to the assumed properties of the system. Now, the system itself is whether if it's LTI, it's LTI regardless of the input. Um, I'm not sure I'm getting the heart of your question. Maybe we could talk about it offline because I'm not sure I quite get it, what the question is.
I was more confused about the time invariant part because cosine is changing over time, but I'm guessing in the summation, that whole thing just turns into like a value instead of something that changes with time, maybe.
Okay, so the point is, if we did a shift in time on the input, we would see a shift in time on the output, which would exactly say that the system itself is not changing with time. So I think what you're doing is you're seeing the time dependence here, and and in a way it's an easy possible mistake to make is, well, we're not describing the system here, we're describing the output. Now the system itself is, all we're doing is we're saying it is LTI. We do have an example coming up for a system LTI, but I would argue that the time dependence in the input doesn't mean the system is time dependent. It just means when you put a time dependent signal into a system, you expect to get a time dependent signal out, whether that system is LTI or not. Am I getting the heart of the question?
Yeah, I think so.
Okay. I mean, if not, then we can always talk about it a little later. Okay, so a point that conclusion you can draw from this is you notice that the pattern of this is very similar. It's pretty much the same as what we did for a single sinusoid. It looks like what was happening is each of the frequency terms is being amplitude-wise is being scaled, and you're phase shifting by exactly the transfer function phase at the frequency in question. Notice the frequency in question, n omega naught, is the same frequency here. So the transfer function is evaluated at that frequency also. So, it's really what we saw happen for a single sinusoid at a certain frequency is happening just in each of these terms. And it's not really, not really terribly complicated by the fact that you have a series, I don't think. Oops, I didn't want to do that. Let's see, let's go back. Okay, so we did that. Okay, let's go down here. Okay, so for the trig basic. Now for the trig basic, the ideas are almost, you can almost talk through them. You could argue that here's your input, and the input is going into the LTI system, and so you're going to apply the operation to each of these. Okay. And we already saw what happens. Basically the ANs and the BNs are constant, so the operation ends up on only the time dependent part. We've already analyzed what happens with a cosine. We analyzed what happens to a sine, even analyzed up here at the top because the C0 is also obtained as the A0. So we would get A0 times the transfer function at 0. That takes care of the DC term. And then we would move that operation past the sum, past the coefficients in front, just operate on the cosine part. And I'll remind you that we've actually looked at that in a very simple way. The only thing that happened is you reproduce the cosine, have to throw in the magnitude of the transfer function at the frequency in question, and add in the phase shift at the frequency in question. And that worked for the sine. And we did the same thing we had another case where we looked at a sinusoid, pure sinusoid in the form we see here. And again, the operation on that sinusoid of the system, then you evaluated the transfer function at the frequency in question, and that would be n omega naught. And then the only thing happened was you phase shifted that sine by exactly the phase shift associated with the transfer function at that frequency.
It's Tom.
Oh, it is time. Okay, all right. Well, we're wrapping up here. I believe I'll be putting some notes. I know I'll be putting notes for the Fourier transform chapter there before Monday, and so I'll be looking for them. And I'm here for additional questions if you got them. don't hear any questions. Okay, so we'll be picking up on page 32 of these notes on Monday. Any questions? Not hearing any questions. Okay. You know, I mentioned my policy. If you had questions, bring them up. If not, I'm just going to go ahead and sign off here. You have a good weekend, hopefully. Let's see, where are we on this? All right. Last chance. Any questions?
Yes, sir.
Yes.
Actually, about the lab on the other class, did you
Okay.
did you get it?
I've actually been a little tied up. I'll be checking my email today. I don't remember seeing it. How'd you send it?
Yeah, I sent it to your Petra email.
How'd you send it?
Yeah,
No, how did you send it?
to your Petra email.
Through what?
Your Petra email address.
My Patriot email.
Yeah,
Well, I'm glad you're asking me because I didn't see it. Are you sure or did you use the email that's on my syllabus?
yeah. Hal Piper was petra.edu.
Okay, well, I will double check, but if you don't mind, resend it. Double check the syllabus and make sure you use that email that's on there.
Sure, I will do that.
Because I was there just this morning and looking at the email. I did not see it from you, but I will look again. Okay.
It's gonna be
I would
fun.
suggest you double check, make sure you use the email that's in my syllabus.
Okay, sir.
Because I think UT Tyler has, I think it's like 2 different email systems. Anyway, we can talk about that offline.
I will resend it.
Excuse me?
I will resend it.
Resend it. If I did not receive it, I don't remember seeing it. Let's put it that way. If I missed it, I missed it, but I don't remember seeing it this morning. I will look again.
Okay, sir.
Okay. Any other questions? All right. Well, I'm going to sign off here.